Hi, everybody. Today's video, we are starting circular motion. This is the extension of two-dimensional kinematics because to move in a circle, you need two dimensions, right? So this is going to be the last bit that we go over with two-dimensional kinematics, but we'll do it using two-dimensional vectors, and we will use vectors a lot in our discussion. So first, let's talk about uniform circular motion. Does the velocity change for an object undergoing uniform circular motion? So the term uniform makes it sound like it's going to go the same speed no matter what, right? And that's usually true. We are going to talk about things that are moving in a circle or moving in an arc that we can call part of a circle, right? But they're going to use a constant speed. However, if we look at this vector here, right? Let's zoom in here. Okay, we have this vector. That's the vector that the car is traveling at that instant. Now, if the car is over here, the car is now traveling at this instant. Now, those arrows should be the same length to show that they have the same magnitude, same speed, but there is something different about them, right? They're facing in different directions. Now, velocity has two components to it. It is speed with direction, right? That's how you define the velocity vector. So if the direction changes, that is a velocity change, right? So yes, the velocity does change if we have uniform circular motion. It may not change its speed, but if it changes direction, that means that the velocity changes. And now an even more important question, is there acceleration? So if you have any kind of change in velocity, that means that you will have a change in speed or direction, which means there's acceleration, right? If velocity changes for any reason, speed or direction, acceleration must do that, right? So they're actually a very common acceleration that we'll talk about, which is called centripetal acceleration, or you can call it radial acceleration. Okay? It's the same thing, but a different name. And that is what causes this velocity to change its direction. That acceleration is along the radius. Okay? That is centripetal acceleration or radial acceleration. Now, since it's accelerating along the radius, that is what causes this velocity to change its direction. Now, for us to change the speed, right? Let me draw another vector over here. Let's say that we have a vector coming off at this direction, right? But then we have a changing vector that wants to change that arrow coming off at a 90-degree angle. Now, that will change the direction of that arrow, but that doesn't mean that it's going to change the magnitude, right? To change the magnitude of that vector, you would want to be in the same plane. So if this vector is at an angle, right? It is not at a 90-degree angle. For example, it has an x and a y component. Let's say arbitrarily x and y, right? It does have an angle along the x-axis. It's not just a right angle. So this, it looks like, would actually start slowing down. It would decrease that red vector because it's opposing it in the x direction. If it opposes it in the y, that's not going to affect the magnitude in the x. It may change the direction of the vector, but it's not going to affect the magnitude in any way. Remember, there is a fundamental rule in physics that any force that's at a 90-degree angle can't affect anything. Let's see, how should I word that? It can't affect that axis. So let's talk about projectiles, right? Let's say we have a type 1 projectile. Launches right here. It's got velocity in the x, and it's going to come down and it's going to splat, right? It's got acceleration in the y, which is negative 9.81. We've talked about that a lot. But that doesn't change the velocity in the x at all because they're at 90 degrees, right? Anything that's perpendicular to a vector can't actually affect the magnitude. Now, it can affect the direction. Now, if you look at this, when that object hits, the velocity vector is now at a different direction, right? It's v in the x direction component, right? That component will still have the same value, but the overall vector has now changed directions. Same for this guy over here. If we keep this along the y-axis, okay, that means that if this were velocity, like we're talking about with the car, it may change direction, but it won't change the strength of that vector in that direction. Just like we have over here, Vx is Vx at the beginning and the end of a type 1 projectile because acceleration in the x is 0. There's nothing to change it. Same here. There is no acceleration in the x direction, or in this case, if it's a circle, that would be the tangential direction, right? A tangent is a vector that only touches at one point. So if we have a tangential velocity, but a radial, meaning it's along the radius at 90 degrees, it can affect the direction, but it can't affect the magnitude because they don't have that axis in common. All right, let's move on. Oh, it looks like I marked on that slide. Let's move on and let's talk about this derivation, right? So, centripetal acceleration. Centripetal acceleration has a rather complicated derivation. Okay, so we're going to use this image, right? And I'm actually going to zoom in and focus on this one. Let's move you over here. Come on now. There we go. So this is going to use some geometry to do this. But let's say that, and we'll use this triangle as well. If we took this VF, right? Here, let me explain the image first. We have the position along an arc starting from the origin. Here's your origin, right? If you look at the point relative to the origin, it has this vector Ri from origin to this point A on the curve, right? Now, after some amount of time, it has now moved to point B on another point along this curve. That is shown by the position vector Rf. Now, if you want to find the change in position, you would say that is delta R. And let me prove to you that what we're showing is true. Okay, so if we take the vector Rf and we're going to, let me snag that vector. I'm going to move it over here. Now, if we subtract, so I'm going to put the head on the other end of this vector, we're going to subtract Ri to show change in position. Right? So if we want to find the change in position, remember that's a difference vector. That's the vector subtraction, not vector addition. But if we were to find this vector here, right, that would be our delta R, which if I did this right, hopefully I did, I can move this on up. Bingo, it fits, right? So when we do these delta vectors, that is vector subtraction, which is not anything unusual for you guys. If I come up here and I ask for what is delta x, well, you would say that's the final position minus the initial position, right? If you want delta v, you would take vf subtract v naught. That's not anything new that you guys haven't done before. Now we're just doing it with arrows, right? So our delta r vector up here, right here, delta r, that is the change in position over some amount of time, right? Now, what we're also looking at is the change in position over that, or I'm sorry, the change in velocity over that amount of time. We have this velocity vi and velocity vf. If we were to do vector subtraction, you can see over here, you would get this change in velocity delta v, right? So we have a delta v, we have a delta r. So what we're going to do is we're going to use some triangles, right, to get this. It's kind of like a proof, which in my opinion is the worst part of geometry. But to show that this is all congruent with the other vectors, we're going to have to prove that, right? So let me prove it. We have this vector rf, and I'm going to say that that continues off in this direction, and then vector ri will continue off in this direction. Now, we already have delta r that is closing that triangle. What we'll do is we will, let me make sure that I draw this appropriately. So we have the VI comes across here. Then I need to mirror that. Oh, whoops. Oh, goodness. Oh, boy. Isn't that fun? All right, so let's come back down here. So I'm going to continue that VF across there. I'm going to get that straighter. VF. Bingo. Okay. So let's look at this imagery here. We're going to call, so we have point A and point B, right? Here is, whoops. That's point A. That's point B. Okay. Here in the middle, we'll call that point C. Up here and here, we have two new points. We'll call this D, call this E. Okay. So if we look at these triangles, okay, we're going to say that the triangle, here I'll write A and B just for good measure. I won't write it over the other B though. All right, so let's say that the triangle ACD is congruent to angle or triangle BCE, right? That means that ACD is congruent to BCE. I'll draw that a little bit better. There we go. So those triangles are congruent. So what this tells us, all of that work just shows us that mathematically we are able to say that if we had the triangle relationship delta V divided by the magnitude of V, right? Because remember, the magnitude has not changed, only the direction. That could be also, there is a relationship to say that the delta R over magnitude R are equal, right? That ratio, that relationship between the change in velocity and the magnitude of velocity is the same as the change in position over the magnitude of the position vector. So we're looking at a couple different triangles here. That means that we have this, I'll put the blue for position. The long legs are the magnitude, and then the top of that triangle is the change in R. We could say that let me erase that guy there. That would be congruent, or I guess that would be equal to the relationship of this triangle if delta V divided by the length of that V vector, that would be the same as dividing the delta R divided by the length of the r vector. All of that is from this triangle relationship, which is not a huge deal to say, right? That's just a common rule with circular motion. As long as the vector didn't change, right? As long as the radius is not changing its length and the velocity doesn't change its speed, it's only changing direction, then this holds true, which is almost all of uniform circular motion, right? That's kind of the definition. So all that to be said, let's now work through the math. Okay, so let me change the pen here. So we've got delta V divided by V equals delta R divided by R. Okay, so what we're trying to do here, this is a centripetal acceleration derivation, right? So we're trying to work our way towards acceleration. So let's get that in terms of things that look like acceleration. So let's solve for delta V, right? Delta V would then equal delta R times V over R. Now, if we divide both sides by delta T, that could start meaning something. So what we're going to do is we will divide delta T to both sides. Delta V over delta T is acceleration, right? So if we have delta V over delta T, this could equal delta R over delta T times V over R, right? So let's say that acceleration equals delta V over delta T. We can say that acceleration equals delta R over delta T times V over R, right? This isn't something totally new to you guys, so we didn't make leaps and bounds, right? Now, this part is going to be tricky. So what we're going to say is that for this scenario here, if delta T, now we're basically just taking, the derivative. We're going to say as delta T approaches 0, delta R becomes what would be delta S. So delta R is the change in radius. Delta S is the arc length, right? So if we look at this, I'm going to erase all of this so that you guys can see what I'm actually talking about here. So if we look at this drawing, zoom that in, delta R is this vector here, right? That is delta R. Delta S measures the entire distance, right? So we don't want delta R if we're trying to say velocity, right? So if we look down here, you can see that we've got a delta R, delta T. You would think that that would equal velocity, but it doesn't, because if we look at the path the velocity took, right, the velocity didn't jump across that blue line. It went across the arc. So if we take the derivative, if we make the assumption that delta T is approaching 0, then we could say that that delta R is now a delta S over that time, right? We wouldn't say that velocity changed across the blue line. If we take that derivative and look at it instantaneously, piece by piece, you could see that it actually went across the arc instead, which is honestly, making that assumption doesn't change the math a whole lot. All it does is say that instead of delta R, we're going to call it delta S. So all of that to be said, we now end with, let me change that. All that to be said, we will now say delta S over delta T times V over R equals acceleration, right? So if now we say that velocity equals delta S over delta T, because it doesn't equal delta R delta T in this scenario. It did not go across that straight line, it went across the arc. So if we make this assumption, we can now say that acceleration equals velocity times velocity divided by the radius, right? Which gives us this equation, acceleration, and this is centripetal acceleration. Centripetal acceleration derivation equals v squared divided by r. So that is a equation that you guys will use for circular motion. Centripetal acceleration is v squared over r. It's a common equation that we'll use all throughout circular motion. We will use this equation frequently for the rest of the year when we use anything that has to do with centripetal acceleration, because this is not going away after this chapter. If I went too fast on any of that, or if you need any of that explained over again, just rewind and listen to it again. Hopefully that'll clear things up. All right, next. Now, so there's an alternate centripetal acceleration. What if you don't have the linear velocity, right? There is something called angular velocity, okay? So angular velocity is something very different. Angular velocity is if you measure the rate that you're going around in a circle. So I'll redraw that arc real quick. Say we're going around this circle, right? And we have these radius vectors. We've got r naught, rf, right? But instead of knowing how fast we are moving tangentially, right? We don't have this velocity vector that's showing the tangent rate of change. What we really have is we have the rate that we are going around the circle. Okay. That is shown by an omega, which is really just a curvy w. So omega, right? Omega is measured in radians per second. I know that in calculus, you guys will get your calculator in degrees, and then all of a sudden a radian problem pops up, and then you forget to switch it over, and then you screwed up your whole problem. That happens in physics too. Isn't that exciting? You will have theta down here that will almost always be in degrees unless we're talking circular motion. But you've got a lot of thetas that will be in degrees, but when we do circular motion, we're going to keep things in radians. And we can go over in class how to change from degrees to radians, radians to degrees. There are tons of videos about that one. But angular velocity, right? Angular velocity is radians per second. It can also be shown as revolutions per second, right? Or that is also in America commonly called RPMs, right? Revolutions per second. Or I'm sorry, revolutions per minute is another possible unit that you can use. RPMs or revolutions per second. That's just saying revolutions per second, revolutions per minute. But that is what angular velocity is, right? So how you can find angular velocity. Angular velocity is the velocity divided by the radius, right? You're basically taking that linear speed and dividing it by the distance from the origin, and that will give you your omega. This also means that if you want to go back and forth, you could say that velocity is omega times r, right? Just solve for the other variable. Now, if we want to find the other centripetal acceleration equation, right? We have AC equals v squared over r. But what if velocity was omega r? Let's plug that in. We have omega r quantity squared divided by radius, right? So that means that we have omega squared r squared divided by r. One of those r's will cancel, and you get omega squared r. So now we have two equations. AC is v squared over r, or AC is omega squared r. The difference in that division and multiplication. So that's the alternate term, right? The units for angular velocity, right? That's number two. They can be kind of tricky. If your problem gives you information in revolutions per second or revolutions per minute, go with it. If it doesn't, you have to use radians because your math is going to give you radians per second if you use these conversions. These conversions, unless you've got something special with your velocity that's going to give you some revolution information, because usually that velocity is just meters per second. So if you take meters per second divided by meters, right? Let's look at that real quick. Omega is velocity divided by radius. So that means that we have meters per second divided by second. If you're dividing a fraction, you can always multiply by the reciprocal. So you could say meters per second times 1 over seconds. No, I'm sorry, that's not the reciprocal. Times seconds over 1. Right? So then, what am I doing wrong? I'm sorry. I knew something was missing. I apologize. Radius is not measured in seconds, it's measured in meters. So to multiply by the reciprocal, I was right, you've got 1 over meters. So those meters will cancel, and that gives you the unit 1 over seconds, or more commonly, seconds inverse, right? So that is the real unit for angular velocity. And the reason that is because radians is not a real unit when we do unit analysis. You don't actually include radians in that math. Seconds inverse is the true unit of angular velocity. Now that can be used for revolutions per second. If you need to use revolutions, you can figure that out using your radius and convert your radius and your velocity into the appropriate terms. But you want to keep your omega in radians as long as possible. If your problem uses revolutions, use revolutions. But you want to keep everything in radians. Okay. All right. Radians per second is also a lot easier when you need to do your trig and your calculus, because there will be trig and calculus that comes up with some of these problems. Having to deal with revolutions per minute and revolutions per second kind of gets in the way of that. Radians were developed at the same time as calculus. Radians were actually developed for calculus. So this is already made for your math. You don't need to complicate your math by using revolutions. Okay. So that is circular motions part 1. I know that had a hefty derivation in there, and then we started talking about congruent triangles. But now we have several new equations that we can start using for problems. So on the next video, we'll talk a little bit more about what centripetal acceleration means in the force world with centripetal force. But then we'll do a couple practice problems so that you guys can get more familiar with centripetal acceleration.